The first presentation is from Işıkkent, İzmir, Türkiye. Evrim Yalçın will be presenting. Hi, Evrim.
Hi, hello.
Hi.
It took time to go to the
Yeah,
breakout, sorry.
it's okay.
Okay, so let me share my screen. Hello, everybody. It's good to see you again here. Okay, let me share my screen. Okay.
It's okay, yes.
So now can you see my
Yes.
presentation? Okay,
Yes. You
great.
can do it presentation mode, maybe?
Yeah, I will continue there. Thank you. Okay, so I'm going to share a study that we made together with Hasret Hoca, Özgün, and Emre Bey together. I think last year I presented this topic, RLC topic here, but this year I'm going to present the study and the results of the study we carried out. By the way, I'm Evrim Yalçın. I'm from Işıkkent Eğitim Kampüsü, İzmir, Turkey. We are an IB school. We are implementing IB PYP here. I'm working as a PYP coordinator and at the same time kindergarten principal this year. So in our study, we looked at it's a kind of mixed method study. We looked at the solution quality and causal reasoning in primary science education. So first I can share why system thinking matters in primary science. Actually, it helps learners move from event-level explanations to structural understanding. And it is essential for understanding complex environmental systems. That's why it is really important in primary science, especially in PYP. And we realized that, unfortunately, there is no published study found at the intersection of system thinking, primary education, and IB PYP. Then we said, why not? Why we can create one? So we started working on that. And my other question is why this study fits the IB PYP. As you may know, PYP is an inquiry-based learning process, and it's transdisciplinary learning, and it is derived from real-world context, authentic real-world problems. And it is conceptual understanding, reflection, and collaboration. So system thinking fits very much on PYP. Then why RLC? RLC situation, we are dealing with that for 3 or 4 years, I think, in our school. In fourth grades, our central idea is the conscious use of limited resources affects the future of societies. So we will be looking at the resources around us and how we should use them consciously, what happens to them, and how it affects the societies. We inquired into the resources. The physical foundations of human civilization are finite. This is the understanding of the resource behind the resources inquiry. Then we moved on water as a limited resource. Which we really need to put stress on that. And it was around World Water Day as well. So we were planning to implement that part as well. Then in our third line of inquiry, we looked at sustainable living and social impact. And then why RLC? We found this study in system thinking website, and it affects us a lot. We were like, we thought maybe we can use that idea, that story of RLC's shrinking in time. So from 1960s, it was a great place. Then in 2020s, it's in critical stage, and the transformation impacted us a lot. So here, the shrinking of the RLC was not a sudden natural disaster, but a decades-long environmental transformation. So it is done by human intervention. That is the sad point of it. That's why we wanted our students look at that in detail. Then they inquired into the RLC first, and they realized the diversion of river water because of the cotton fields. The countries decided to divert the water to the fields because of the cotton production. And then the water level in the sea is falling, is decreasing. Then it caused ecosystem damage, right? And it caused loss of fish stocks, and after that it caused severe health problems, and of course economic decline, population displacement maybe. So we want our students be aware of this. Then in our study, our students were age 9 and 10. We had 52 fourth grade students in our school in İzmir, Işıkkent Eğitim Kampüsü. And our unit was Sharing the Planet Inquiry Unit. And we put those students into 24 collaborative working groups. And our question was, how can we move young learners from monocausal linear reasoning and teach them grasp the structural system thinking? Because at that age, children they generally think, linearly, just this causes this causes that. That is the nature of the students. But we want them to think differently, more deeply, in a systematic way. That's why we carried out this study. The aim of the study is to examine the potential of a stock flow interface to support system thinking competencies among young children. We asked, does stock flow interface, using stock flow diagrams, does it improve solution quality? How do students represent causal relationships? What is the relationship between causal complexity and operational solutions? Those were our questions when we are studying this. Then we introduced them this stock flow interface and in Stella Architect. This interface included a stock flow diagram, a behavior overtime graph, and a regional map. This was very interesting for our students to play with. I say it play with because they really played with that. Before they made some guesses, estimations, and they just put the numbers in the system, and they saw the graph changing and the real water level is changing in the program, and they liked it a lot. They played with that. And it affected. I will come to that later. I will show you 3 pages from their workbook that they are working with, booklet they are working with. We talked them, we found out the real story of Aral Lake, what happened. And then we asked them some estimation questions. What do you think the water level will be in 2020? Or what do you think the level will be in 2050? Or what about 2070? They wrote their ideas there. Then we showed this diagram to them, and we asked them, what changes do you see when we make evaporation 10? They looked at the graph, the stock flow, and the map, and they wrote their findings. And then we said, let's change time from 1960 to 90 and run it again. What do you observe? Or another question, what should we do so that the water does not decrease while evaporation continues? So they played with the diagram, they wrote their ideas. Then we started inquiring into what would happen if Lake Aral were restored. What would change? So they started answering with their group. Then 1 week later, during that week, of course, we didn't leave this topic. We were still continuing inquiring into some resources, some limited ones, unlimited ones, blah, blah. Then we showed them the Sustainable Development Goals, 6 and 14, life below water or clean water and sanitation. They started searching on that website, and they found out what UN is trying to do to save water in the world. So we asked them, considering the information you have examined about, what can be done to save Lake Aral from drying up? Write it down. So they started thinking their ideas. Then we analyzed their answers into two phases, I can say. One is solution quality. We looked at the answers, the ideas, and we grouped them according to two groups. One is operational solutions, like responses targeting system structure, thinking about inflows and outflows. And the other solutions were commonplace, like more generic, more awareness-based, surface-level responses. So we grouped them. Then we analyzed their answers, and we transformed the answers into causal diagrams. From these diagrams, we analyzed the variables students identified, the number of causal relations they drew, and the overall complexity or relational depth of their reasoning. Then we found out during interface use, when they are using the Stella architect, students produce more operational solutions. Later, when they responded without direct use of the tools, their answers became more general and commonplace. This was interesting for us. I mean, after 1 week, without the interface in front of them, the students' reasoning shifted dramatically. Their reasoning changed into more general. For example, before their ideas were like reducing cotton production, revitalizing rivers, blah, blah. But then after 1 week later, I can say, their ideas were more common. For example, awareness campaigns can be made, or we can establish advocacy organizations, or we can ask for foreign aid, or we can make documentaries to inform people about this situation. So the findings or the interpretation of the study and conclusion, we realized that stock flow tools supported structural reasoning in the moment of use. That's sad. You know, we really want them to continue that thought, but it's not continuing. And the tools show strong promise in IBPYP science, but these gains appear to require repeated exposure and sustained scaffolding. That is very important. And then we came up with this idea after the study. System thinking cannot be of one event. It's not a separate activity that we need to do in our classrooms. Yes, it works a lot, but to raise a generation capable of managing our planet's finite resources, we must embed structural reasoning into the DNA of education. We must do this, we must implement this system thinking approach in every area of our curriculum. Fortunately, IB lets us do that. We are very free in IB, so we can play with that. But we need to continue using it without breaks to build that understanding and that thinking structure in our students. We need to explicitly instruct learners on causal link formation, moving them from listing variables to diagnostic systems, and assess the structural relevance of the intervention, not just the volume of awareness it generates. So system dynamics, as the last sentence I can say, system dynamics is a powerful yet fragile tool for primary science. It requires sustained integration, not just isolated exposure. That is the idea we came up with in our study. And I hope this time this study will be published and it will be one and unique study at all. We are believing in it. And really, it's good to see the result of it, the effect, the impact on students' thinking. It's amazing to see that. In our school, our aim is putting more system thinking in our curriculum from K to 12. That is important. We're generally using it in primary and kindergarten these years, but now our idea is implementing it more and we can map it in our curriculum, and I'm sure we will see more better and deeper and greater results. Thank you very much for listening. I don't know if I made it so fast.
No, it was very good actually. Thank you, Evrim, for this
Thank you.
comprehensive study and for sharing with us. So we will take the questions every two presentations, and now I will move on a video presentation due to time zone inconvenience. This will be a presentation from South Korea. Let me share.
Hello everyone, my name is Leana Kim, South Korea. This study was conducted under the guidance of Professor Sung-Chun Kim. Today I would like to share findings from a year-long classroom study titled The Emergence of System Thinking in Early Elementary Education. The study explores how system thinking begins to emerge among third grade students through sustained classroom practice, rather than asking whether young children can master system thinking. This research asks a different question. How does system thinking gradually emerge when children repeatedly experience it in meaningful context? We live in a world shaped by complex and interconnected problems, such as environmental crisis, social conflicts, and systemic change. These problems require circular and relational thinking. However, education often assumes that young children are too young to grasp abstract concepts like feedback loops and time delays. As shown on this slide, traditional education treats thinking as moving from point A to point B, while real-world systems operate through feedback delay and interdependence. So, the central question of this study was, can a year-long intervention shift third graders from seeing events to noticing underlying structures? Emergence takes time. This study was conducted over one full academic year from March to December. 37 instructional sessions, authentic classroom setting, iterative learning cycles rather than one-time instruction. Instead of teaching system thinking as abstract theory, students encounter the ideas repeatedly through games, storybooks, discussions, and visual modeling. The goal was not immediate mastery, but gradual cognitive transformation. To support abstract thinking, students used visual scaffolds. Four main tools were introduced. First, behavior over time graphs to visualize change. Second, causal loop diagrams to map feedback relationships. Third, the iceberg model to move beyond visible events. Fourth, stock and flow models to understand accumulation and rates. These tools functioned not as assessment instruments, but as thinking supports. They helped the children externalize ideas that were still forming internally. Now I will present the results. The first developmental pattern observed was a shift from reacting to events toward organizing structures. Using storybooks such as The Penguin's Contract, actually this is a Korean translation. The original title is The Tip of the Iceberg. Students learned to distinguish between observable events and underlying patterns. One student said, "When I imagine the iceberg model in my mind, things become organized." This indicates that the iceberg model became a cognitive framework, not just an activity. Students began using structure as a way to interpret experience. The second pattern involved understanding time delay. Students moved beyond immediate cause and effect reasoning. For example, one student explained, the cause already happened, but the result appears later. This shows emerging awareness that outcomes do not always occur instantly. As you know, this is a key feature of system thinking. The third pattern appeared during peer conflicts. During recess time, students recognized reinforcing feedback loops in escalating arguments. One student said, "If it continued, it would get bigger." Here, systems concepts became tools for self-regulation, not just academic understanding. Systems thinking began influencing social behavior. Through the story, The Noisy Puddle, students explored ecological interdependence. A student reflected, trash doesn't just disappear. It goes around and affects nature. The concept of connection expanded into moral reasoning. System thinking became a lens for environmental responsibility rather than only a technical concept. A key finding is that system thinking does not appear suddenly. It develops along a continuum. First, vague intuitive sense, and next, partial understanding, and last, explicit articulation. The goal is not perfect terminology, but orientation toward relational thinking. Following Vygotsky's perspective, cognition developed first through external interaction. Drawing diagrams allowed students to express thoughts they could not yet fully verbalize. Importantly, accuracy of diagrams mattered less than the thinking process itself. Concepts such as delay and accumulation contradict children's everyday intuition. Therefore, learning required repeated exposure across context. Games, stories, physical activities, and reflection. This created what I call a slow learning architecture. Cluster A to F, shown on the slide, represent the step-by-step stages of the system thinking concepts. Another important finding was emotional engagement. All students reported that lessons were enjoyable. Because activities were playful and meaningful, abstract concepts remained memorable. Emotion acted as a catalyst for cognitive retention. Based on these findings, systems thinking literacy can be redefined not as technical mastery, but as a habit of mind. It represents a shift in how students see the world, not simply what they know. Students began habitually looking for connections, structures, and delays in everyday life. Three implications emerge. First, design. System thinking requires cumulative learning, long-term learning. Second, assessment. Evaluation should focus on changes in reasoning and explanation, not test scores. Third, age assumptions. Even third graders can develop proto-system thinking when learning is experiential and grounded. This is the implications for future education. In conclusion, System thinking is not merely a problem-solving skill. It is an epistemic shift, a new way of understanding reality as interconnected structures rather than isolated events. This study suggests it is possible. Even young learners can begin to develop system thinking through sustained learning experience, and it is verifiable. These developmental changes can be observed and documented through qualitative evidence. And last, it is vital. Most importantly, system thinking is an essential competence for understanding the complex problems for our time. Thank you very much.
We thank Leana for sending this video to us. And now we can have a quick question maybe for Evrim or for the video. So, okay, thank you again.